Hi everyone, and welcome back to another episode of Dr. Kyle Explains, your YouTube channel where we go through GCSE science content quickly and easily. Today we're going to be going through giant covalent structures. So if you like the sound of that, please remember to give the video a thumbs up, subscribe to the channel, tell your friends about it, grab some pen and paper, and let's go ahead and jump in. Okay, so some key content first about giant covalent structures. So giant covalent structures have high melting points. They are all solid at room temperatures. All the atoms are linked together by strong covalent bonds. Now, this is often a topic pupils sometimes get confused. Covalent bonds are always strong, but what often happens is there are weak intermolecular forces between the molecules, making them have low melting points. Now, the molecules themselves can have weak forces between them, but the covalent bonds are always strong. Now, in the case of giant covalent structures, as we'll see in this video, the structures are very, very large and they're all connected with strong covalent bonds, meaning they all have very high melting points because of these strong bonds. So just make sure we really understand the difference between simple covalent molecules and small molecules and giant molecules. The three main structures you need to know about are diamond, graphite, and silicon dioxide. Okay, so the three main structures then. So here we have got diamond, just at the bottom here, one to the left. In the middle we've got graphite. And then over on the right hand side here we have got silicon dioxide. Now we're going to go into these in a bit more detail in a second. Main things I want to highlight to you are diamond and graphite are both made from carbon. So they're essentially elements, whereas silicon dioxide is a compound. Now the other word you may come across is the word allotrope. Now an allotrope is essentially a chemical or a compound that is made up of the same elements but in a different form. In the instance of diamond and graphite, they are both allotropes of each other because they're both made from carbon, but they're in a different form. So here we've got diamond and every carbon is bonded to 4 carbons, whereas in graphite every carbon is bonded to 3 carbons. So they're both made out of carbon, but they are still different substances. One's diamond, one's graphite. This is actually one of my favourite things of like facts of chemistry to think about, that just one bond difference has a huge effect on the properties of these two chemicals. And in fact, diamond obviously is really quite rare and very, very expensive, whereas graphite is incredibly common and very, very cheap. And all the differences is just changing one chemical bond. So if it's bonded to 4 carbons, it's diamond, really expensive. Bonded to 3 carbons, it's graphite, very, very cheap. So the term there, when it's just a different form of it, is called an allotrope. Remember, both made from carbon. Okay, so what I've done is I've summarised the 3 giant covalent structures in a table format for you to go through and have a look at the properties. So giant structure here, structure and properties. We're going to do diamond first, then graphite, then silicon dioxide. So again, here's the structure of diamond. Now, you will not have to learn the pictures here. You will not have to be able to draw them, but you will have to see them in an exam and be able to identify them. So there might be like a box next to it or a line to draw to it to show that that's diamond. So you do need to be able to identify these by looking at them. So when it's drawn like this, that's diamond. Now in diamond, giant covalent structure, as we already know, the title of the video, and as I've already said, 4 carbons are bonded to each carbon. So every carbon here, if I just highlight this here, if we look at this one in the middle, it's connected to 4 other carbons. So every single one. So here we've got 1, 2, 3, 4. Always 4 carbons. Now you might be thinking, well, what's going on here? There's only 1, 2 here. And this is just a small segment of the diamond structure. So there is still another bond coming off here, another one going there, connecting to another diamond, and then it's repeating on further as you go through like this. So every carbon is bonded to 4 carbons. Here's what's known as a tetrahedral structure, and a tetrahedral structure is literally where you have again 4 carbons bonded to each other like this. So it's like methane is also in a tetrahedral arrangement. Strong bonds, lots of energy needed to break the bonds, high melting point, and it has a hard, rigid structure. So it's often used for things like saw blades. If anyone's parents or guardians is a builder, if you go and ask them, they might tell you that they've got diamonds actually encrusted on their saw blades, and that's to help them cut through concrete and stuff. Diamond is actually the hardest naturally occurring substance on the planet because it is a very, very strong compound arranged in this way, really, really rigid structure. So it's used to cut through things. Okay, next one then is graphite. So graphite, again, made out of carbon, and this is the structure shown here. Now, just to remind you, you do not have to draw this, but you might have to identify it in an exam. So you might have, again, have a little line to draw to it, or a box to tick next to it, or you might have to write underneath it that that's graphite. So giant covalent structure again, 3 carbons are bonded to each carbon this time. So here, if I just show you the one in the middle here, we've got my carbon here, and then it's connected to 1, 2, 3 carbons. If we look at the bottom here, we've got 1 here, and then 1, 2, 3 carbons. And again, even on the side here, this one here is obviously only bonded to 1, 2 carbons, but again, the structure carries on, bonded to 3. So it's just showing you a small section of this giant structure. Now in graphite, it's arranged in layers. And so what this means is each layer of graphene, and we will go through what graphene is in another video. Graphene is essentially one layer of graphite. You have these layers building up on top of each other. So thousands and thousands of layers of graphene to make graphite. Now, these layers are not actually bonded covalently together. They have these weak intermolecular forces between these layers. So these kind of lines here are representing these weak intermolecular forces. Now, what that means is the layers can literally slide between each other. Now, this makes graphite good for pencils. So I'm sure you're aware graphite is in pencils, so the lead is made out of graphite. But what that means is when you put the pencil nib on your paper and pull it across, you've literally got layers of graphite sliding off onto the paper. And that's why when you get a rubber, you can rub it out, you're rubbing those layers away. Nice and easy. Now, interestingly, graphite can conduct electricity. And that's because we're bonded to 3 carbons. Now this means you have 1 delocalized electron per carbon, and it can conduct electricity because those delocalized electrons can carry the charge throughout the whole structure. Now again, this is a topic that pupils often get muddled up. Pupils often get this muddled up with ionic compounds, where the ions are free to move and carry the charge. Whereas in graphite, we have delocalized electrons that can carry the charge throughout the structure. Please make sure you are absolutely certain why graphite can conduct electricity and how ionic compounds can conduct electricity, because they're both different ways and you need to be able to do that in your test. Okay, lastly then we've got silicon dioxide. Now hopefully we can see silicon dioxide has a very, very similar structure to diamond, and that means it has very, very similar properties. Still a giant covalent structure, but this time it's made out of silicon and oxygen. So each silicon is bonded to 4 oxygens. Again, we've got strong bonds, and so lots of energy is needed to break those bonds. Therefore, it's got a high melting point. Exactly the same properties as diamond. Okay, so I'm going to go through some questions now. Please feel free to either listen to the answers, or I would really encourage you to have a go at these and then pause the video and then see what I come up with as my explanation. So why is diamond used on drill tips? So first of all, I would say diamond is a giant covalent structure. Now, as soon as you remember that, you need to remember giant, you need to think strong, high melting points. Now, melting points are probably not going to help you too much on a drill, but what does a drill need to be able to do? It needs to be able to drill into things like concrete, bricks, stone, even wood. It's quite difficult to drill into sometimes. So therefore, it needs to be hard, it needs to be strong. So diamond is a giant covalent structure. It has strong covalent bonds and a hard, rigid structure. could maybe talk about the fact that it's in a tetrahedral structure as well. So hard rigid structure, so lots of energy is needed to break bonds, making it good to be used in things like saws and on drill tips. Okay, have another go at one. So why is graphite used as a lubricant? Pause the video, have a go. Okay, so hopefully we know a lubricant can be things like oil or grease. They can be used in like door hinges and things like that. And graphite can be used for that. It's often sometimes used for keyholes in order to get a key inside a lock when the lock's jammed. So why is graphite used as a lubricant? So lubricants, you've got to remember, are slippery. So what do we know about graphite? We know it's got a high melting point. Is that going to help us with the fact that it can be used as a lubricant? Probably not. We know it can conduct electricity. Is that going to help us as a lubricant? Again, probably not. What do we know about graphite? So I'd probably start off with graphite. Sorry, let's start that again. Graphite is a giant covalent structure. Probably always just start with that sentence just to remind us what it is. It is arranged in layers. Now that is important. Why is that important? In between the layers are weak intermolecular forces. And so what does that mean? The layers can slide. And so if they can slide, slippery, they can be used as a lubricant. Okay, so let's have a think. Explain why graphite can conduct electricity, but diamond can't. Okay, so again, let's think about this. What properties do we need for graphite in order to conduct electricity? Is the fact that it's arranged in layers going to help us explain why it can conduct electricity? Probably not. Is it the fact that it's got a high melting point? Or if the diamond's got a high melting point, going to explain either why they can or can't conduct electricity? Probably not. What do we know then? So again, graphite has a giant covalent structure. Covalent structure. And then I'd say each carbon, just going to write C for carbon, is bonded to 3 other carbons. So there is a spare delocalized electron that can carry the charge through the structure. So that's going to explain why graphite can conduct electricity. Diamond, every carbon bonded to 4 carbons, so no delocalized electrons. So if I really quickly, I'd say that's probably give us our 4 marks now, but really quickly, if I just show you on the side here, if we do carbon, I'll dot and cross diagrams again. Remember, if you haven't seen my video on simple covalent molecules and dot across diagrams, please do go back through my channel and just have a quick look. So I've got 4 carbons here. So what's the rule? Carbon is in group 4, so therefore it needs 4 electrons. So it's going to have 4 pairs. So we go 1, 2, 3, 4. Hopefully we can see that on the video. So we can see no spare electrons there. If we bond carbon to 3 carbons, just really quickly, just over here, carbon, carbon, carbon. So again, carbon is bonded to 4, it's in group 4. So we've got 1, 2, 3, 4. Then we put our pairs in there from the other carbons, and we notice we've got that spare electron there. That's why it conducts electricity. Now again, just to remind you, pupils get this muddled up all the time. It's a really common question people get wrong. Do not get this muddled up with ionic compounds that can conduct electricity because they have ions that are free to move. That is completely different to delocalized electrons. So please make sure to go through my other video on ionic compounds and the properties in order to be able to answer that question. Really well done if you got that right. Okay, lastly then, so we've got, why does silicon dioxide have a high melting point? Again, pause the video, have a go. So, silicon dioxide is a giant covalent structure. Now again, that word giant should pop in your head straight away. What do we know? High melting point. So if something's got a high melting point, the bonds have got to be strong, haven't they? So it has strong covalent bonds. Every silicon is bonded to 4 oxygens. And so lastly, we would say, so lots of energy needed, or is needed, I should say, is needed to break bonds. Perfect. Okay, so again, 4 marks there in order to get that that question. So please be aware, again, we've gone through things on ionic compounds now, and we've done simple covalent molecules. And if you haven't seen those videos, please do go back through my playlist, have a look at them. Whenever we talk about melting points, so whether they are high or low, if they are high, we say lots of energy needed to break those bonds. If they are low, we say not much energy needed to break those forces. Okay, so please always remember, as soon as you've got that sentence there where it says high melting points or low melting points, you always talk about the energy at the end of your paragraph. Okay, so finally, let's have a look at our tick list then. So describe and explain why giant covalent structures have high melting points / boiling points. Yep, definitely done that. Describe the structure and properties of diamond, graphite, and silicon dioxide. We've absolutely smashed that too. Thank you so much for watching. Please do go through my other videos on my playlist to find more GCSE science content for me to help you get a grade 9 in your science. Remember, if you ever need any help, Dr. Kyle explains. Thanks very much. Bye-bye.